Next, we consider a flat plate called lamina, which uniform density that occupies a region of the plane. We wish to locate the center of the mass of the plate, which is called the centroid of that region. In doing so, we use the following physical principles. The symmetry principle says that if the region is symmetric about a line, then the centroid of that region lies on that line. So if the region is reflected about the line, then the region remains the same, so its centroid remains fixed. But the only fixed points lie on that line. Thus, the centroid of a rectangle is its center. Now, moments should be defined so that if the entire mass of a region is concentrated at the center of mass, then its moments remain unchanged. Also, the moment of the union of two non-overlapping regions should be the sum of the moments of the individual regions. Now, suppose that the region is of the type shown here in figure 13. In this case, 13a. So here is our region. Now, the region lies between the lines x is equal to a and x equals b, and it's above the x-axis, and then beneath the graph of f, where f is a continuous function. Now we divide the interval ab into n subintervals and endpoints x subscript 0, going from x subscript n, and equal with delta x. So we choose the sample point x subscript I to be the midpoint of that subinterval. And that is, we're going to take x subscript I minus 1 plus x subscript I and divide it by 2. This determines the polygonal approximation to the region shown in the figure 13b. The centroid of the ith approximating rectangle is its center, and so its area is taking the function of x bar times delta x. So its mass is the following: rho times f of x bar times delta x. Now the moment of the region about the y-axis is the product of its mass and the distance from c subscript I to the y-axis, which is x bar. Thus we would get the following formula. We would get the moment for y times the region, which is equal to rho times f of x bar delta x times x bar, which then becomes rho times x bar times a function of x bar times delta x. Now, adding these moments, we obtain the moment of the polygonal approximation to the region, and then by taking the limit as n approaches infinity, we obtain the moment of the region itself about the y-axis. So then when we get the moment for y is then going to equal the integral that goes from a to b, factoring out rho times x f of x dx. Now, in a similar fashion, we compute the moment of the region about the x-axis as the product of its mass and distance from ci to the x-axis. In this case, we're taking rho times f of x bar times delta x times 1/2 of f of x bar, which is equal to rho times 1/2 of f of x bar squared delta x. Now again, we're going to use the Riemann sum to take the limit to obtain the moment of that region about the x-axis, and then we would get the following integral. It's going to go from a lower limit of a to b, factoring out rho, 1/2 times f of x squared dx. So just as for systems of particles, the center of mass of the plate is defined so that m times x bar is equal to my and m times y bar is equal to mx. But the mass of the plate is the product of its density and its area. So the density times the area is equal to the mass, which then gives us this integral. And so, in order for us to then solve for x bar and y bar, we're just going to take the moments about the y-axis over the mass. So we're going to divide those two integrals, simplifying rho, which then gives us this integral. And then the same thing for y bar. We're going to take the moments for x divided by its mass, which then gives us the following. Now, we cancel out the density, so the location of the center of mass is independent of density. So in summary, the center of mass of the plate, or the centroid of the region, is then located at the point x bar, y bar, where x bar is equal to 1 over a of the integral going from a to b x f of x dx, and y bar is equal to 1 over a going from a lower limit of a to b 1/2 f of x squared dx.